Okay. Good afternoon, everyone. My name is Tanesha Chiu, and today I'll be doing my research proposal presentation on the investigation of entrance and exit doses from linacs and CyberKnife and the impact on skin dose. My supervisors will be Pejman, Jonathon, and Warwick. I would like to give a special thank you to Pejman for always answering my incessant questions and always being available for the many meetings that we've had. So here's an overview of my project aims. I will be investigating skin dose on 6MV FF and triple F photon beams, 6MV electron beams, immobilization masks, tattoos, and exit dose / backscatter. And this will be done using CyberKnife and linac machines. Some background on skin cancer. Skin cancer is the third most common cancer to be diagnosed in 2021 in Australia. 11.2% of all new diagnosed cancers is estimated to be skin cancer in Australia. And the three main types of skin cancer are malignant melanoma, two non-melanoma skin cancers known as basal cell carcinoma and squamous cell carcinoma. Some background on skin dose. Instead of UV radiation, radiotherapy involves the use of X-ray photons, which is the cause for induced skin cancer from radiotherapy. Skin is the largest organ in the body and therefore is the most visible target for reactions induced through radiotherapy. Some examples of acute skin reactions include alopecia, which is the loss of hair. This starts at 15 to 20 gray within 3 to 4 weeks of radiotherapy. Next, we have erythema, which is a rash. This starts within 2 to 3 weeks of radiotherapy. And lastly, dry desquamation, which is the peeling of skin within 2 to 4 weeks of erythema. I was going to include some pictures, but I think some people are grossed out by those things, so we'll move on. The skin dose is measured at the basal layer at 0.07 millimeters, which you can see here, and this is also known as surface dose. The use of MV beams has the added advantage of the skin-sparing effect. For triple F beams, there is a beam output which increases to hundreds of thousands of monitor units per minute and will shorten treatment time. FF beams have a large number of low-energy photons in the beam due to scatter. This weakens the beam hardening effect and therefore increases patient skin dose. Electron beams. Electrons may be useful in this investigation as it may interact with the tattoo ink as it contains iron oxides and metal salts. So, an overview of CyberKnife versus linacs. What are the improvements that CyberKnife allows over linacs? Frameless radiosurgery. It can monitor and track patient positioning continuously through the use of online images in order to find the exact position of the target within the treatment room coordinate system. The dose delivery accuracy is in the order of around 1 millimeter, and this is done through image-guided systems. Do you want me to continue? Pejman, the click. Frameless radiosurgery to the spine, lung, prostate can be done using the body skeleton or surgically implanted fiduciary markers as reference. What are the important differences between CyberKnife and linacs? So firstly, the size of the beam is different, so therefore beam scatter will also be different. There is less skin dose due to collimation than in linacs. There is a smaller field, so therefore there will be less scatter compared to larger fields. There's no flattening filter, so therefore we are expecting less skin dose and out-of-field dose. And lastly, for a square 3x3 field, cone absorption of radiation allows the field dose to be more sharp compared to linacs due to MLC leakage. The significances of my project are the following: creating awareness of avoiding extra skin dose. An important note to make here is that TPS only calculates skin dose to about 25% accuracy. The consequences of extra skin dose, such as secondary skin cancer induced through radiotherapy, making note of accidents that may occur in radiotherapy that are related to skin dose and can result in skin damage. And lastly, the different techniques in order to avoid skin dose will be addressed. So here's an overview of my project plan. As mentioned before, I'll be using FF and FFF beams at 6 to 10 MV, and CyberKnife will be solely 6 MV. Again, I'll be measuring skin dose, but also skin dose from tattoos. And here are the different measurements I'll be making. So field size out of field dose for both tattoos and for normal skin, and skin dose on thermoplastic mask and couch dot. So that'll be the backscatter. An overview of the methods I'll be using. Again, as mentioned earlier, I'll be using 6 to 10 FF and FFF photon beams for the following, with the exception of tattoo ink, which includes 6 MV electron beams. I'll be using gapromic film in order to measure entrance and exit doses. Film can be placed in 3 ways. The first will be over a tissue equivalent phantom. Secondly, we can place the film between the phantom and the couch. And lastly, using a thin layer of uracil over the film, which will be placed on top of the phantom. Next, I'll be measuring skin dose of thermoplastic mask immobilizers in order to measure the effects upon entrance dose. And this will be done using film with and without the mask. Lastly, using tattoo ink, which will be infused in different tissue equivalents in order to measure the effect of entrance dose. So an example of this will be, again, using a thin layer of uracil, and this will be laced with ink, placed over a film and on top of a phantom. So here's an overview of the publications I'll be mentioning today. This first publication is a general overview on skin dose. This publication mentions immobilization masks. This one is the very specific publication on tattoos and electron beams. This last publication mentions couch tops. So for an overview of what factors increase skin dose, we have field size. As field size increases, skin dose can increase anywhere from 20 to 85% of Dmax. Block trays, these are fixed to the linac head. Oblique beams, so angles that are greater than 55 degrees, can reach 50% larger dose. Off-axis position. Surface dose decreases at the edge of the field. And lastly, backscatter. This is material behind the patient, such as a couch top. The next publication mentions immobilization masks and how they can result in a buildup or bolus effect, and this leads to increased skin dose. This publication used 2 different brands of masks, MedTech and Run-Through, at 6 and 15 photon beams, and measured skin dose with TLDs. At 15 MV, they saw no effect, but at 6 MV, interestingly, they saw 20% increase in skin dose. Some key factors that may increase skin dose that they've listed are thickness. So thicker the cast, the more increase in skin dose. The pattern of the mesh, the smaller the holes, the bigger the increase in skin dose. And lastly, the angle of incident beam. So vertical incident beams showed an increase in skin dose more than tangential beams. The next publication summarizes tattoo dose. So for tattoos, which contain high atomic number elements in the ink, it would be interesting to analyze what is actually causing the skin dose. So we have here they analyze 4 colors: yellow, blue, black, and red. They use 6 to 20 MV electron beams, measuring surface dose perturbation with an ion chamber. For yellow ink, they saw that for 6 MV electron beams, 1.4 to 6% of dose perturbation, and this was consistent between 6 to 20 MV. Lastly, for blue, black, and red ink, they saw 3% dose perturbation for 6 to 20 MV beams. And lastly, skin toxicity, which results from attenuation through couch tops. Carbon fiber couch tops can attenuate up to 15%, and the usual value is around 2 to 5%. Factors that influence this attenuation include field size. So for example, a 5 by 5 centimeter square field leads to attenuation difference of 1%, but a 10 by 10 centimeter squared field leads to attenuation of 7%. And lastly, beam angle. Attenuation can increase to the order of 4 times for beam angles as it increases from 0 to 70 degrees. These are the references I used, and thank you very much for listening. Marshall?
How come you're only using electron beams for the tattoos?
Thank you for the question. Funnily enough, I actually prepared some slides. So your question was, why are you only using electron beams for tattoos? So, electron beams may interact with the ink and create more skin dose than anticipated. But the reason why we aren't using electron beams en masse is because the dose gradient for electrons falls off quickly, and here there's a diagram with the dose gradient for 6 MV, and the mass itself will disturb the dose profile and no longer be uniform, since electron beams are usually used for surface lesions. Keaton?
I had a question. I think towards the start you mentioned that skin dose was measured around 0.07 mils beneath the surface. Is there any particular reason behind that?
Good question. So here I have once again prepared something earlier. Why do you measure skin dose at 0.0 millimeters, aka the basal layer? So anatomy of the skin can change both on the same body and also in the same location. So for example, for breast cancer patients, you would ask them to raise their arms because there are often skin folds in the chest area. And the basal layer is the most radiosensitive layer of the epidermis.
So I noticed in the publications there are a few different measures that they use to measure the skin dose. Is there any particular reason that you've chosen film for your project to use to measure that skin dose?
Great question. I have also prepared a slide for that. Why use radiochromic film over TLDs? Or any other dosimeter for that matter, aka ion chambers. So for radiochromic film, it is water equivalent and TLDs are not. Same for ion chambers. TLDs and ion chambers are too big in size to measure skin dose compared to film, since skin dose is usually measured at around 0.7 millimeters. And lastly, radiochromic film has a uniform thickness.
Any other questions?
Rachel?
Why is the treatment planning system not good for calculating skin dose?
Wonderful question. So why is TPS not good for calculating skin dose? TPS uses kernels, and there is a big difference between tissue and air. So TPS needs more space in order for it to calculate skin dose properly. An alternative that can be used is Monte Carlo-based TPS, but the drawback is computation time. Yes?
Comment to that. What is the resolution for TPS? What is your
size, the minimum voxel size. Sometimes it is in the order of 1 or 2 millimeters. And if the calculated dose there would be an average. So in that case, you can go 0.07 mil if your box size is that big. Just that.
That's another great point. Martin, questions?
So in a linac beam, normally incident, no masks or anything, what parts of the radiation contribute most to the skin dose? What parts of the beam?
So if you're talking about, say, FF and triple F beams, then I believe I actually have a slide for that. What results were you expecting of FF and triple F beams? Flattening filters create scatter in the form of low energy KV photon beams. So this creates a difference in energy spectrums, and this leads to extra skin dose. So hence for all 3 different variations, we would follow this trend. And as you mentioned, without the mask, and that last point is kind of irrelevant to your question, but.
What about the, what particles are in a photon beam, an X-ray beam? Just photon?
I believe so.
I'll look into that. But there's another question. You talked about the tattoo, but people put other things on their skin, like creams and sunscreens has titanium in it, for example. Do you think they might also have an impact?
So while I was doing my reading for my project, I did see that they mentioned topical creams in order to make like the skin toxicity reactions better for the patient while they were in treatment, but that did cause a similar bolus effect as, say, for a tattoo, but I haven't read too deeply into that, but I'm sure I'll have something more to say once I start to research.
Okay, Tanesha. That was very interesting. It's taken via Zoom. So I'm not quite at the best angle to see all your slides, so it might have been a side section that I couldn't read. You're talking about the interaction with decorative tattoos, not position marking tattoos, or both?
So specifically decorative tattoos that are already pre-existing on their skin and not the tattoos that they use for reference.
Okay, thank you very much. Very interesting.
No problem.